Hi everybody, hopefully this works okay. I am coming to you live from the classroom here, Z351. Feel free to stop by if you want to say hello. Hopefully this works. We can adjust the times as I talked about in class depending on what people really want. I don't have to do it from here. Right now there is no one else here, so maybe this is not a great time. I do see there's a couple people watching online. All right, well, we're going to talk today about the process of science, which is our topic for this module, and some of the basics, and a little bit of an intro to the readings. And then on Wednesday at the same time, we'll go into a little bit more detail on those readings. In the future, we won't always do it at this time if that doesn't work for you, but I'll look forward to talking to you this week about to try to see what works. Okay, so let's talk a little bit about some definitions when we talk about science. Now, I'm going to kind of assume that in your former science classes you've talked about the basics of the scientific method. You have a basic idea of experimentation. In fact, I know you do because we did this last week in lab. I know you know how to set up an experiment, look at results, learn from that experiment, try something else, formulate a hypothesis, look at some evidence, things like that. So I want to talk about or focus more on some misconceptions, things that people often get wrong when we talk about the process of science. All right. So for me to start off, I think a big one here are a couple definitions that we should talk about right away. And those are law and theory. Now, in science, these terms are really often misunderstood. I guess by people who aren't in science, they're misunderstood because we also use these words in non-scientific contexts. And so the thing that kind of always people think when I ask, what is a law, what is a theory, people tend to say, well, a law is something that is proven and absolutely true, and a theory is something that someone's thinking about and may or may not be true. And that is false. That is the wrong definition. All right. In science, a law is just a set of observations that seem to happen over and over. So, you know, like the law of gravity comes up because you can make observations of all different attractive forces between matter, whether it's things falling down to the earth, whether it's bodies in space moving, and you always get similar outcomes. And so you can set up a rule that says when this happens, then this happens. All right, that's true with things that we'll talk about a little bit later in the class, like gas laws, where we say if we compress a gas, this is what happens to the volume, this is what happens to the temperature. So another way of kind of summarizing that is thinking about it as what happens, the what is happening. This thing happens, then this happens. That's what happens. And so that's a law. When you take those observations together, you set up this law that's like, okay, whenever this happens, this happens. So for example, we might set up a law of students coming to class because we notice that every time it rains, students are late to class. Right? It's raining today, so I don't know if that's actually true. I just made that up. All right, but notice what that doesn't tell us. That doesn't say why. It kind of implies that the rain causes students to be late, but it doesn't actually say that. It just says when this happens, this happens. And these two things are somehow connected. They're correlated. So then in science, a theory is the why behind all of that. So if the law is the set of observations, a theory describes reasons behind those observations. So if we go back to our student example, so we have this law where when it rains, students are late. So now the theory is, well, okay, what's actually happening that's causing this? What's the causal relationship here? What are the other phenomena that are going on? So is it because it takes longer to put on a raincoat? Is it because you drive slower in the rain? Is it because the rain makes you tired and you want to lay down and not come to campus? What is actually the reason behind these things? So this we could think of as the why. And importantly, neither of these is like more important or more true than the other. Both require evidence, right? Both can be found false if there's enough contrary evidence. So you might have a law that works and then you have to go back and say, that's not quite right. Good example of that is Newton's laws of motion. So the laws that govern how things fly through the air and all of that sort of thing, forces and velocities and accelerations and whatnot, those aren't false. I'm not saying those are false, but those were found in the 20th century to not really work in certain situations, particularly with very, very small things, very, very large things moving really fast. And we had to use other corrections, like relativity, to describe the motion of those things. Right? So depending on the evidence, you can say that a law is no longer quite valid and it has to be corrected in this way. And the same thing with a theory. A theory is not just an idea that is not proven yet. A theory describes reasons, and it can be proven with evidence too. A good example of that is atomic theory, the theory that matter is made up of atoms. It's not terribly controversial. Most people would say it is absolutely true. We have pretty clear, direct evidence that matter is made up of atoms. But that doesn't make it a law. That's the theory, because when we assume or when we know that stuff is made up of atoms, then we can predict all of these other things that happen, like everything we do in chemistry. All right, so put a star around this thing or whatever. It's something that is really hard to kind of deprogram yourself from remembering from what you think it might mean. A theory is not just an idea that someone has that's unproven. A scientific theory has a specific meaning. And in fact, a scientific theory is much more powerful than a scientific law. Because once you have the theory, you can now explain all of this other stuff and you can make predictions based on the theory, whereas the law is just a set of observations and you're not really sure why it's happening. So often in science, the goal is actually to come up with the theory. The goal is to find the theory that explains what's going on. All right, I'll pause for a second, see if there's any questions in the chat or on Teams. You can always send them over if you're watching live. If you're watching later, you can still send questions, but I probably won't be able to respond right now. Okay, so now I want to jump over to a document that's in our lab today. Here it is. So at the end, I'm asking you to engage explain how you engaged in practices of science during the lab investigation. Now these practices are developed by the National Science Teachers Association, and it's kind of a more general description of scientific practices and behaviors that we want people to learn as they take science classes. And as you're in a science class, these are the sorts of things that you should be able to do or that you should be working on as we move through this class. All right, some of these you've done, of course, last week in lab. So asking questions and defining problems. What does that mean in a scientific context? Well, in a scientific context, asking questions is things like, why is this happening? What is causing this? What do we want to find out? Why is this happening? Last week, you did an experiment. It had some things that happened during the experiment, some color changes, some temperature changes, some gas evolution. And so some questions that you could ask are, why is this happening? What's causing the gas? What's causing the color change? These are things that you all did as you went through that activity. Second, developing and using models. This is not something we necessarily did last week, but one way to solve this problem might be to think about another simpler system and use that to model the more complicated system. So maybe we draw how these things are coming together. Maybe we use a computer simulation of the molecules or the atoms and see what's happening there, try to make some guesses as to what's going on. Later in the semester, we're going to use molecular models. Right? These things are fun. You put these things together, make different types of molecules, and that will be an example of using models because we can't manipulate atoms directly. We can use a model, and we can manipulate the model of the atom. All right. Planning and carrying out investigations. You definitely did this last week. So you did, whoops, lost our thing here. All right, so you did an experiment that was just directed, like do this, do this, do this, do this, and then you had to figure out how to redesign the experiment, and that becomes more of an investigation. So how are you going to identify variables or parameters, things you can change, and then come up with a new experiment? Analyzing and interpreting data, we didn't do much of last time, but we'll certainly do more of that in the future. So what if, we talked a little bit about this in one of the sections. What if we had more precise measurement tools for that lab? What if we could weigh things? What if we could measure volume, measure how much gas was evolved? Then we could really get some data, and we could say, well, okay, when we decreased the sodium bicarbonate by 3 grams, we saw this specific change in temperature by degrees that we measured with a thermometer, or we saw this difference in gas evolution because we measured the amount of gas that comes out. So often when we do these experiments, we want to make measurements and then have data that we can interpret, and that starts to get us on the road to making these conclusions. All right, mathematics, computational tools, those will come in. Everybody's always scared of taking chemistry because they think that there's going to be too much math, too much calculation, and I understand that. But it's a great tool to be able to understand some of these relationships in data. And I know from our conversations last week, a lot of you are in mathy fields like accounting, so we'll do some math. We'll do it together. We'll do it recognizing that you're not experts in scientific mathematics, but we'll work through it, and then hopefully you'll see why that can be such a useful tool. And then explanations and solutions. I don't really understand designing solutions. That sounds almost like a businessy sort of term, but certainly constructing explanations goes along with theories, what's really happening that's causing these things. And then the last two deal with communication. So once you have this evidence, you have to make the case that this is what this actually proves. And then if you were to, say, present your findings at a scientific conference, people would argue with you. Not in a mean way, hopefully, sometimes in a mean way, to be honest. But the idea is that they would say, well, okay, you said this, but I'm not sure that's totally right because your data doesn't quite show what you think it shows. And then you have to say, well, actually, I did these other experiments, and so it shows that this is actually the solution. So when I think the lab last time talks about claims and evidence, you can't just say that you think sodium bicarbonate causes the gas to be evolved, because somebody could say, okay, why? What's your evidence that that's actually happening? And so you'd go back to your observations and your experiments, and you say, well, I did this experiment and it showed this. I did this experiment, it showed this, so on and so on and so on. And if I take all of these together, I have a body of work that shows that this is the evidence for my claim that the sodium bicarbonate causes the gas evolution, as an example. All right. And then the last one, I don't know if you can see it over my head here. We have to be able to communicate this stuff to everybody. Part of it is within the scientific community, so you find something, you have to let other people know about it. Some of it is also outside that community. So you find some stuff and you want other people who are not scientists to know about it. So that's something that we work on as well. How do you share this information, this knowledge with people who didn't do this? So keeping a good lab notebook is part of that. And just writing and understanding that communication is part of that. All right, so you'll work on this stuff more this week. We have a couple more labs that allow you to do some investigating, some experimentation, and then you can think about how you did these things, how you did these scientific activities. Okay, so that's most of the new information for today. On Wednesday, we're going to talk about those 4 readings that I posted. Now, rather than go through all of them right now, I think I'd rather do that in person. So when I see you all well, I guess I'll only see half of you today, half of you on Monday. So let's introduce them now, and then we can do that. Whoop. Got too many teams here. Okay. Back into our files here. So there are 4 readings that I've posted here in Teams. They're kind of in whatever order, but the first one actually is a textbook. It's a full textbook, so don't read the whole thing. But it's about different ways of knowing things. We talk about the scientific method as a method of knowledge acquisition, but it's not the only method of knowledge acquisition, and it's not the only valid method of knowledge acquisition. We can say it works well in certain situations, but another way of getting knowledge is from community, from people who already know that stuff, passing it down to you, from exploration in a different sort of way. And so one way that that's been thought of and talked about and studied is looking at indigenous science or traditional indigenous knowledge, where communities found a lot of the same things about their environment, about the natural world, found a lot of the same things that that Westerners found, Europeans found later, using more what we think of as scientific tools, but they were really doing the same thing. I shouldn't say they were doing the same thing. They were effectively finding knowledge about their communities and their environments using a different way of doing that that is not exactly science. So it's interesting to compare and contrast those methods, realizing that they're both valid, they both lead to valid knowledge acquisition. The other 3 readings are more traditional science writings. So the first one comes from a book, Science for All Americans, that was written in the 90s as a way of communicating science and some of these ideas. So if you want more of like the textbook definitions of the stuff that we're talking about, that's a good place for that. The third one is probably the most fun to read of the whole thing. It's a transcription of a speech by the physicist Richard Feynman, who was a really great animated speaker who people love to listen to talk. So it's not at all dry and textbook-like. It's a speech about science. And so as he got more famous as a scientist, he started doing public lectures where he would talk about things that weren't just his research, but just kind of general ideas about science. And this is from a collection of those called The Meaning of It All. And if we pull this one up here, he gave a series of lectures here, and this particular one is about the uncertainty of science. So another thing that we want to talk about when we talk about the scientific method that we'll look at in a second is uncertainty and the null hypothesis. And so this is his kind of musings on that. And there's some really interesting ways that he put this. And when I read this back when I was in college, it really helped clarify my thinking about science and about the world and about how I wanted to find things out. So I always enjoy discussing this with students, and this is definitely a good one to look at. And then the last one is a bit more difficult to read, but people have asked me for something like this in the past, so it's a good, if you're interested in this sort of thing, it's Albert Einstein, the famous physicist, talking about science and religion, and he kind of reluctantly talked about these things. He was, again, as he got more famous, people asked him, well, what do you think about this? What do you think about this? As these conflicts were becoming more popular. This one's a little bit difficult to read just because remember that Einstein is writing English as a second language. And so the English in here is somewhat German styled grammatically. It's of course been edited and it's correct English, but it's maybe not the way a American speaker would or American writer would write. But it's kind of clarifying his thoughts on the relationship between science and religion and how knowledge acquisition works in those domains and why it's important to think about these things. It's very, as you might expect, it's pretty not broad. It's very specific to Jewish and Christian theology and the way that science, the interplay with science with those. And so if you're interested in that specific relationship, this is a great way of exploring one of our great thinkers' ideas about that. I probably won't say a ton about this on Wednesday because it doesn't quite address like these specific goals of what science is, but it is interesting if you think about these ideas and you want to know what Einstein had to say about it. All right, so let's jump back to our notes here. And the other definition, a couple other definitions that I want to put in here. Before we leave. The first is uncertainty, and I don't really need to define this because it's not different. We don't have a special scientific definition of uncertainty, but it is really a key to science. One of the things that differentiates science from other types of knowledge acquisition is that we always leave the door open for uncertainty. We can amass evidence that seems almost certain that a particular thing is true, but we always leave room for more evidence to falsify that thing. Now that doesn't mean that if there's a ton of evidence in favor of something, one little inconsistency is going to bring the whole thing crashing down. That's not how it works. But what it means is we're never so certain of something that we start ignoring evidence to the contrary. We welcome evidence to the contrary. We experiment, we theorize, and we think we have something figured out, but then we always go back to the evidence, and if the evidence starts to point in the other direction, we leave that uncertainty, that doubt open. It's another good word here, right? So we're never perfectly certain. We're never absolutely certain of something. So when I say, for example, that I have done a bunch of experiments and it seems from the evidence that the sodium bicarbonate caused the gas evolution in the reaction last week. And I write about it and I present at a conference all about it. But then some other people start doing some experiments and their experiments don't agree with what I found. They replicate my experiments. I didn't do anything wrong, but I wasn't thinking about some other factor maybe. And so as they're doing their experiments and they're figuring something out, they come back and say, yeah, we did a bunch of these other experiments and it seems like Joe was wrong. Actually, it's the calcium chloride that's responsible for the gas evolution. By the way, just aside, neither one of those is exactly right. But this is how science is done. So I might do some more experiments and I might find more evidence to what I thought in the first place, or I might start finding that these other groups were also right. And I never want to be so sure of myself that I ignore that contrary evidence and just say, no. I know the answer is here. These people don't know what they're talking about. Right? I always want to have that open mind to doubt my conclusions. Now, again, that said, it gets scientists sometimes into trouble. And the reason is that when we communicate to other people, we communicate with words that emphasize this doubt. So we say, when you read a scientific paper, the results will say things like, this may have a strong effect on this, right? It may have a strong effect. Not it does, or we know that it has an effect on this, but it may have an effect on this. We say things like, it seems that this is happening, or this affects this. We use this kind of language of uncertainty. And so when that goes out into the non-scientific world, sometimes it makes people think that we don't really know, that Who knows, right? We saw a lot of this happening with COVID, especially toward the beginning, which was a great example of how this process works, where the people doing real serious science were not coming out with absolutes. We were saying, oh, it seems like maybe you should wash your hands, seems like you should wear masks, maybe wear these types of masks. And then as more evidence came in, some of those ideas got reversed, right? Like we thought you had to wash your groceries and stuff. And then we found out that COVID really doesn't transmit from surfaces. And so people were saying, what are you talking about? Well, how do you not figure this out? You're telling us one thing one day and then a different thing the next day. And the answer is, that's how science works, right? You find your evidence first, you make some preliminary conclusions based on that evidence, but then as more evidence comes out, you may have to revise or completely reject your initial claims because the new evidence is stronger, is more complete. And so that happens all the time in science. And sometimes as scientists, we don't communicate forcefully because we understand that there's that uncertainty there, but when we talk to non-scientists, sometimes that gets us into trouble. So now that you have a little bit of science education, you can think about that a little bit more. When you read these quotes from scientists that seem a little cagey, that seem a little uncertain, you can think, well, do they not know, or is this just that language of uncertainty because they might get proven wrong later? All right. I think that's enough for today. So I will see half of you in about half an hour in our usual lab. I'll see the rest of you on Wednesday. Please read through those documents to help clarify your thinking, and they will help you to address the goals. Again, the module reflection should be done by this weekend so that we can discuss it next week. And you can start booking those appointments to meet with me next week. For this first meeting, it can either be in person or online. Either way, we can meet virtually, we can meet in person. If it's during our lab time, I would prefer to meet here in person just because I'll have that all set up. But other times, if you'd prefer to meet virtually, that's fine. Just set a note when you leave a note when you set your appointment up. The midterm and final ones will be in person, but this one's more just like a check-in to make sure you understand how things go and everything's okay. So you can start booking those appointments. And as I mentioned in class, if your schedule is more flexible, please try to take one of the times that is not during our lab, because some people that is the only possible time that they can meet. And so if you can leave some slots open for the folks who really need to meet at that time, we would appreciate it. All right, I'll see you in a bit. Hopefully this posts and you can watch it later if you weren't watching live right now. Otherwise, I will see you soon. Bye.